Now this experiment where an event A occurs or does not occur, right, or you have each, right, where the experiment only tells you you are only concerned with, right, success or failure, right. When I say okay, let me say e.g. coin, such as coin tossing, right. That is to say, you are only interested in success or failure or head or tail, right, where let us say the probability of head is P, which is, or probability of, let us say, success. Some on each trial, on any one trial, right, probability of succeeding is this P, right. Obviously probability of failing is 1 minus P, right. This is a very standard situation. Supposing you consider n trials, right, what is the probability that you get exactly k successes, right. Or k head, this is heads, H stands for heads, right, k heads, or i.e. probability of k successes, right. What is this? It turns out if you look at any one pattern of success failure, it is going to be p power k 1 minus p power n minus k. Well, that is only one pattern, like one specific string of 1 0 1, like that. If you, let us say, 1 is success and 0 is failure, right, any one specific string, such string is going to have this probability p to the power of k 1 minus p power n minus k. This is right. How many such strings are there? There are n choose k such strings. And each string is exclusive of any other string. So you are perfectly justified in adding up all these probabilities, right. They all have the same probability, they are all exclusive of each other. Again you have, right, this combinatorial coefficient coming here, this n choose k. If you do it for some small value of n and k, you will understand, those of you who are seeing it for the first time, why this is n choose k, right, because that is the number of positions that you have for putting the k successes in the overall string of n, right, n trials that you have. So each trial you mark as either success or failure, right. How many ways can you choose k out of n? It is n choose k. If you have, for example, 4 you are interested in 2 successes out of 4 trials, it is 4 choose 2, which is 6, and you know how to count those 6, right. It's how many ways can you distribute 2 zeros in 4 points? 6 ways, etc., etc., right. So I am not going to elaborate this any further, right. You people who studied combinatorics already, right. So I just want to point out that these are 2 distinct places where combinatorics appears in right at this level in the first course, right. This leads to what is called the binomial distribution, and this leads to what is called what, the hypergeometric distribution. These names again are somewhat binomial, at least we can appreciate, because this is a binomial coefficient, right. But the other term which you just mentioned, that is not very important, but the thing is that there is another probability model which is built around this, right. So these are the 2. Then if you continue with this repeating an experiment, right, till you get success or so let us also, since we have a few more minutes today, right, let us look at this geometric model. We should also look at that, right. So this is the binomial model. Right, and once again I want to emphasize that the term binomial coefficients is applied to these guys for obvious reasons, right. Okay, now let us look at the geometric model, which is what? Just do until you succeed, right. Try till you succeed. The same, instead of fixing the total number of trials, right, we are going to keep repeating till we till we succeed, and then count the total number of trials, right. So, when is the first success or first head going to happen? So, here your omega try until so here again independence of the trials is in very much used here, right. The product of these terms is crucially dependent on the independence assumption, right. Each trial is independent of any other trial. So, the probability of 1 0 or success failures that p into 1 minus p, that is obviously built in. So, the same concept we are going to use here. So, i.e. your omega, the capital omega consists of strings like this. Either you maybe I will use okay, I will use h, head tail. You can get head in the first toss itself, or you can get th, stop, when first h or s, success, happens. There is no reason why you should not you should stop when the first h happens. Of course, here you are not stopping, right, in general. Here you are going all the way till n, and you are stopping at the nth trial no matter what. The n, it is possible that you may not get even a single success in n trials here. Here this is, I think we already hinted at this experiment, right, in the first two classes when we talked about how a sample space could contain a countable infinity of points, right. So, there is no upper bound on how many times you might want to keep trying, whereas here this capital omega has exactly how many points? It has exactly 2 power n points there, isn't it. So, here the compound space omega has 2 power n points. Here it is not really a compound space because it is not constructed as the Cartesian, that product of elementary spaces, right. Nonetheless, right, you can look at the probability of this first success occurring at the kth trial, or let us say at the nth trial. This n is not the same as that n, but since I started writing n, I will stick to it. What is this? Turns out that this is 1 minus p to the power of n minus 1 into p, right, for n greater than equal to 1. So, for this space we are going to attach, right, to this h we attach a probability p, to this we attach a probability 1 minus p times p, for this 1 minus p whole square times p, and you can clearly see that the summation of n equal to 1 to infinity of this 1 minus p power n minus 1, this is the standard geometric summation, and this will add up to 1. So, it is a valid distribution, valid probability assignment, right. Please check this out also. It is a very trivial summation. I hope all of you can do, you remember how to do your geometric summations, because it is something which you will need again, right.
So, is it the first success the nth trial or the nth trial?
It is the first success at the nth trial. Could be first trial itself, second trial, third trial, like that.
Yeah, what is the m over
N.
m? Okay.
I do not think I wrote an m, did I? Okay, so the gong is sounding, so I will stop here. Let me review this binomial model again. So, you have n independent trials. So, instead of calling it head or tail, we will call it success, right. Each trial has success probability equal to p, right. That means that probability of k successes in trials and this expression n choose kp power k 1 minus p power n minus k is valid for all k in this range, right, 1 to n 0 to n, right, and how do we show that this sum k equal to 0 to n, this also we want to be equal to 1, right? What is this actually equal to? Why? Because this is p plus this. So this is a check. So these kinds of distributions of probabilities we will encounter a lot, right, down the course, but maybe, right, we'll give them formal names, right, and so on and so forth. This is our kind of first exposure to them, right. So what are we doing? We have a bunch of numbers here, right, just like probability distribution or any other probability, the way we've apportioned it to different sample points, right, except that we have a nice formula in this case, right. So, and obviously all these are not equal, isn't it? They're all, can be very profoundly different from each other, even for p equal to half. If you take p equals half, for example, you get maximum around n by 2, right. We will see all of these things a little later. Okay. So this is the binomial model and it uses these binomial coefficients, right. So the n choose k, that again for the sake of the camera I am writing this is n factorial, this is let me write this is binomial coefficient, right. And I assume that all of you can evaluate this for some right, or write expressions for it for some values of n and k, right. If you have small values of k, you know how to simplify this. So let me not spend too much time on this, right. Now the reason why I introduced this binomial model was to show you how, right, these binomial coefficients or the combinatorial coefficients keep coming up in this business, right. There are at least two different places that we've seen them crop up, right. One is the choosing of m objects out of n or k objects out of n, right. The number of combinations there will again involve n choose k, and this is another place, right, where in all of these n choose k combinations you have a common term here. That's why, right, this p power k again remember times 1 minus p power n minus k is the probability of any particular sequence, right, which has k successes and in n trials. Okay. Now the geometric model, which is very linked to this, right, because the starting point for the geometric model and the binomial model is basically independent trials of an experiment, right. So each here of course refers to the independent trial, right. So similarly you have the same, let us say, independent trials. So here what did we write yesterday? Probability of the first success in what, the kth trial or the nth trial? What did I use yesterday? I want to stick with that notation. Nth trial. What was this? This was 1 minus p and power n minus 1 times p. Okay. So this is even more easily understood than that, because this is straight away, right, seen to be the product of all those basic trial, the individual trials being fail, and then finally ending with a success, right. So this is true for n greater than equal to 1, and in this case, right, you have a countable infinity of points theoretically in the sample space, right, whereas here you had only 2 power n points. So here we again, I just want to say this for completeness, this is a simple geometric series because I mean this is valid because P is a number between 0 and 1, right. So you can add up the series simply for that reason. P and 1 minus P are both between 0 and 1. Okay. Now let us see how there are certain, actually there is one common thing between these two, right. I mean basically there obviously has to be some commonality between the two models, right, and that is the answer to this question. What is the probability there is no success in the first M trial? I want to use a different number, right, a different no success in the first M trial. So you can calculate this according to both models, right, and you should get, what should you get? 1 minus P to the power M, right. I put M here, I don't know why I want to keep reusing N, right. Now why did we, how is it obtainable from both models? They have to give the same answer, right, otherwise the two models will not be consistent. So how did we get this from here? Here of course this is the this is got by putting k equal to 0 and n equal to m, right. M choose 0 is 1 always, right, and if you put k equal to 0, this will drop out and you will get 1 minus p whole power m from here. From here what happens? Well, you get no success at all, it is like 1 minus p, 1 minus p, this is basically exactly the same thing, right. So no matter which way you do it, you have to get, there is only one way of writing this, right. No success in the first M trials is clearly 1 minus p power m, right. The other nice thing about this geometric model is that it is memoryless, right. I am making sure that I do not miss saying this because it is a very important point, right. What do we mean by memoryless model? Okay, before that let me say one more thing. What is the complement of this event? No success in the first M trials. What is the complement of that? In words? At least one success, right? Let me just write that, right? At least one success in M trials, right? And this can only be obtained from here, because in some sense, because here, right, here you are saying I am going to stop if there is one success, but here we are saying that we are going to go for M trials anyhow. So this is actually obtainable from here, right, which is basically 1 minus the probability of no success. So this is going to be what? 1 minus p power m, right. Anyway, so but this can also be obtained from this model if you add up the probability of the strings, right, f, fs, ffs up where go up to m, right. But let's that would be a different kind of a, I mean a very similar summation like this, except the upper limit would not be infinity. So I urge you to go and obtain this number, this expression, this expression both from here and we have just obtained it from here. Okay. Anyway, but the memoryless property of the geometric model, come back to that. What do we mean by this term memoryless here? That is, you do not care, right? Supposing you say that there have been m minus 1 failures, m, just the same m. Given the information that there have been m minus 1 failures, what is the success in the mth trial? It is still p, because the trials are assumed to be independent, right. Probability of success is at mth trial given no success or no success in m minus 1 trials is still equal to p. right, which is the probability of the success at the mth trial by itself, right. So, this again is a theme that we will pick up on later. It has profound implications for the so called geometric distribution that we will be studying at in great depth later on, right. Anyway, so I think for now I think this serves to just introduce the idea, right, of repeated trials, right, and these are the two most important distributions that come out of that, right. Notice that I am not using any language of random variables or anything to describe these, because you must remember that probability by itself is basic, right, and you know, what we do on top of that, the jargon we add on top of that is something else, right. But as of now you can write these things even without using any fancy terms, right. So, do not think that as soon as we talk about binomial model you have to bring in some other concepts, it is not necessary, right.